and welcome back. This is Mo Hasanovic at Indian River State College. Welcome to the lecture number 4 of our fiber optics video series. Today we are going to be focusing on the construction of optical fiber. We're going to be covering a few different topics. We are going to describe the multi-mode and single mode step index and graded index optical fibers. We already introduced the concept of single mode and multi-mode fibers. Here we're gonna go a little further and talk about so-called step index and graded index types of optical fibers. We'll also explain different specialty fibers that are available out there in the practice. We will be talking about the performance advantages of multi-mode graded index fibers. We'll identify 2 basic types of single mode step index fibers. And finally, we will list the benefits of cable optical fibers over the bare fibers. So this slide pretty much elaborates or reviews what we covered in the previous lecture. We are talking about the basic elements of an optical fiber. We already talked about the core as being a light guiding region that's shown here in a yellow color, and we see a few red dots that represent the light transmission or light propagation through the core. And then the second layer shown here in a gray color is going to be the cladding. Then we have a green colored layer that's so-called acrylate coating, and finally the buffer that's not shown in this picture here. So the basic elements of the optical fiber again are the core, the cladding, the coating, and finally the buffer. Let's review a little bit the basic classification of optical fibers. We said that optical fibers can be categorized into a wide category of single mode fibers and multi-mode fibers. Based on the number of modes that propagate through the optical fibers, we can have either a single mode that support just one single mode propagation, and finally multi-mode fibers that can support as many as 100 modes through their core. What is the main differentiation between these 2 types of fibers? We talked about the size of the core. We said that single mode fibers, they have a significantly thinner core that's usually in the range of 8 to 10 microns. As opposed to multi-mode fibers whose core is going to be around 50 to 100 microns. So there's a significantly larger or thicker core size in the case of multi-mode fibers relative to the single-mode fibers. With this slide, we're introducing another classification of optical fibers, and that's the classification that's based on a refractive index. So we are basically looking at the index of refraction of the core and looking how it changes as we are moving from the center of the core towards the edge of the core. So we can basically classify optical fibers into 3 main groups, so-called multi-mode step index fibers, multi-mode graded index fibers, and finally single-mode step index fibers. We are going to be talking about each of these different categories of the fibers, and we're going to look at their basic properties as well as their advantages and disadvantages. So again, the refractive index profile describes the value of the refractive index as a function of the radial distance at any fiber diameter. And we'll see that in some optical fibers, the index of refraction is going to be changing as you are moving from the center of the core radially towards the edge of the optical core. Okay, let us compare the stepped index versus graded index fibers. So in the case of a stepped index fiber that's shown here on the left picture, the refractive index of the core is uniform and undergoes an abrupt change at the core cladding boundary. You can see on this curve that we have a straight horizontal line that represents index of refraction of the core, and then sudden drop down to a different value of the index of refraction as we are moving into the cladding. This is the basic characteristic of a so-called stepped index optical fiber. As opposed to the stepped index optical fiber, in the case of the graded index fiber, we see that the index of refraction is actually gonna vary gradually as a function of the radial distance from the fiber center. So right at the center of the core, we have the maximum of the index of refraction, and then the index of refraction is going to be dropping gradually to a certain value that's going to be used in the cladding. It turns out that multi-mode graded index fibers are superior compared to the stepped index multi-mode fibers, so they have a better superior performance, and we are going to talk about that on the slides that follow. We'll see, what is causing a superior performance of the graded index fibers relative to the stepped index fibers. Okay, so this slide is very important from the aspect of the comparison of the three main categories of the optical fibers. So what we see here are multi-mode stepped index fiber shown on the top, and then in the middle we have multi-mode graded index, and finally on the bottom we have a single mode stepped index type of optical fiber. So let us compare these three optical fibers. The first thing that you can notice is a type of the light source. In the case of multi-mode fiber, either stepped index or graded index, we are using some sort of light source that has a much larger numerical aperture, so it's easier to couple the light into the multi-mode fiber for the simple reason of its core being much larger, much thicker than the core than the radius of the core in the case of a single mode stepped index. So light source that's being used for multi-mode fiber is much larger and it's much cheaper compared to the light source that's being used to couple the light into the single mode fiber. That's basically what has been elaborated on the first two bullet points for each of these fibers. The second important thing to be discussed is the modal dispersion. We talked about the modal dispersion in the previous lecture, and we said that the dispersion is an effect where the pulse undergoes a certain spreading as it propagates throughout the optical fiber. That's what can be seen on the picture here. So each of the fibers they have the input pulse of the same width, but the output pulse that arrives on the other side of the optical fiber is significantly different. We see that in the case of a single mode stepped index fiber, the duration or the width of the pulse is relatively similar to the width of the input pulse. In other words, we didn't have a lot of dispersion occurring during the whole propagation. The simple reason for that is that in the case of a single mode fiber, we have exclusively one mode, so the modal dispersion basically will not occur. However, in the case of the multi-mode fibers, we have multiple modes. So multiple modes, they have a different trajectories in a glass core. So some modes are basically traveling larger distances because they are bouncing back and forth in a glass core more often than other modes. So in other words, these different modes will be arriving at the output of the optical fiber at different times, and that's actually what's going to cause the spread of the pulse, or so-called modal dispersion. Now, what you can also observe here is that the modal dispersion is much more pronounced in the case of the stepped index multi-mode fiber as opposed to the graded index multi-mode fiber. So in other words, the multi-mode graded index optical fiber has a better performance from the aspect of dispersion if compared to the multi-mode stepped index fiber. Reason for that is the way how different modes are propagating in the glass core. So in the case of a graded index optical fiber, keep in mind that here we are talking about index of refraction that is changing radially as you are moving from the center of the core towards the edge of the core. So in other words, it's almost like having different layers of inside the optical inside the glass core, and having different layers with different density would basically cause an extra additional bending of the light. In other words, the light will not be, different modes will not be propagating along the straight lines that are bouncing back and forth, but would be rather curved. So in other words, that's going to affect the total length that certain modes are propagating to the glass core. In other words, they will be coming and they will be arriving at the other side of the optical fiber much sooner than in the case of the modes in the stepped index fiber. So that's gonna basically have an important impact on the total amount of dispersion that's going to occur in the gradient index fiber. So the gradient index multi-mode fiber has better properties from the aspect of a dispersion, because the trajectories of the different modes are better controlled, in the sense that they're better equalized. So if you go from one mode to the other mode, the trajectories, the length of each of different trajectories through the optical core are kind of closer to each other if compared to the stepped index multi-mode optical fibers. We have already discussed the core size in various types of fibers. We said that standard core sizes for multi-mode stepped index fibers would be 50 micrometers or 100 micrometers. Multi-mode gradient index fibers would have standard core sizes of 50 micrometers, 62.5 micrometers, and 100 micrometers. Also 85 micrometer as a size of the core in the multi-mode gradient index fibers is also used. And finally, single mode fibers have a core size that's 8 to 10 micrometers. So there's a significant difference in the size of the core of single mode fibers compared to the multi-mode, either gradient index or stepped index fibers. This slide also indicates the diameter of the cladding. So for each of the three types of fibers, the cladding is usually is about 125 micrometers, as indicated on the top, on the bottom right side of this slide. There's also a picture on the right side that shows the cross section of the optical fiber that indicates basically what is the size of the core for each of the three types of optical fibers. Also, cladding is shown here as 125 micrometers, and finally recording diameter of the core is going to be around 250 micrometers. Okay, so what would be the basic properties of a multi-mode stepped index fiber? So this type of fiber is a simple fiber that consists of two layers of the material. We have a core and we have the cladding. Each of these two different layers, they have a very distinctive index of refraction that's constant throughout the entire cross section of either core or cladding. So where the core and cladding come in contact, we have abrupt change in the index of refraction, sudden drop if you're going from the core into the cladding, as indicated in the picture on the right side. So this distinct difference in the density of glass between the core and cladding would basically affect how fast the light will propagate through either core or cladding. The denser material, the slower the light is going to travel. That's directly related to the index of refraction. So in other words, the core, since it is optically more dense, has a larger index of refraction. The light is going to travel at a slower speed in the core compared to the speed of light in the cladding. Let's look at the multi-mode stepped index fiber from the perspective of the number of modes. So here, since we are talking about multi-mode fiber, we have a number of modes that are propagating along the core, and actually the number of modes that will be propagating is going to be directly, it's going to be a direct function of the diameter of the core and the index of refraction. Propagating modes also would depend on the wavelength of the transmitted light. So in a typical multi-mode stepped index fiber, there may be hundreds of propagating modes, and cladding diameter in this case is going to have a limited effect on the propagation of light. So in the case of a multi-mode fiber, since the core size is significantly large, it's much easier to couple the light into this type of a fiber. So cheaper more affordable light sources can be used, such as LEDs. So we can use light emitting diodes or LEDs to couple the light into the core of this type of multi-mode optical fiber, because already, as we already elaborated, typical size of the cores, typical diameter of the core in the case of multi-mode fiber would be either 50 micrometers or 100 micrometers. What would be the applications of the multi-mode stepped index fibers? So obviously, due to the fact that the dispersion in this type of fibers is more pronounced, these types of fibers will have limited bandwidth capabilities, and therefore would have limited applications. Usually shorter distances would be on the applications of this type of fiber. So if you are a system designer, you would have to consider different factors that would have an impact on the selection of the appropriate fibers. So usually in this case, we are talking about short haul, limited bandwidth, low cost applications where this type of affordable optical fiber is gonna be used. Let us now talk a little bit about different type of multi-mode optical fibers. That would be the graded index optical fibers. So in this case here, we said that the core is made out of hundreds of layers, each having a specific index of refraction. So index of refraction is basically changing as we are moving from the center of the core towards the edge. So the most optically dense glass is going to be right at the center of the core, and as we are moving towards the edge, the optical density of the glass that's been used to make a core is going to be reduced. So again, as we are moving away from the center, each subsequent layer is going to be slightly less dense than the layer within it. So a light ray traveling down the center axis is going to be traveling in the densest region, and it's going to have the lowest speed as opposed to the light that travels closer to the edge of the core, where we have optically less dense material, and we know that if we have optically less dense material, the speed of light is going to be increased. So if we compare the speed of light in the center of the core to the speed of light at the edge of the core, the speed of light in the center of the core is going to be lower than the speed of the light close to the edge of the core in this type of so-called multi-mode graded index optical fiber. So why is it important to have different speeds of light at the different positions along the cross-section of the optical fiber? Well, this difference is not that great, but it's enough to compensate for longer distances that certain modes are propagating all the way throughout the core of the optical fiber. So the idea is to get all the modes to exit the fiber as close as possible to reduce the spreading of the light pulse, or so-called modal dispersion. So the whole process has been of fabrication process of this type of optical fiber has been perfected to the point where the modal dispersion is completely eliminated through the equalization of the modes of different lengths during their propagation. So the light propagates in the multi-mode graded index fibers according to the refraction and total internal reflection, and the gradual decrease in the core index of refraction from the center to the fiber end is going to cause the light rays to be refracted many times, and by doing that we are basically changing the trajectory, we're changing the direction of the light propagation. So the light becomes more refracted, more curved, as indicated on this picture here, and that's going to increase the angle of incidence at the next point of refraction. So we have this curvy type of trajectory that a light is going to follow as it moves through the core of this type of optical fiber. Now, what would be the advantages of graded index multiple fibers? So first of all, the source to fiber coupling efficiency is increased for the simple reason that we're using multi-mode fiber. They also have more insensitivity to the micro bending and macro bending due to this specific characteristic of the core. And the fiber core size also affects the amount of power that's being coupled into the core, and also loss that's been caused by the microbending and microbending. So what would be the important advantages of multi-mode gradient index fibers is listed in a yellow box. So relatively high source to fiber coupling efficiency due to the larger size of the core. It's low loss, it's low sensitivity to the microbending and macrobending, it's high bandwidth, and also its expansion capability. Gradient index fibers are primarily used in local area network topologies that are typically less than 2 kilometers in length. And these types of fibers, as we already mentioned, outperform the stepped index fibers. The parabolic refractive index profile causes multi-mode gradient index fibers to have less modal dispersion, and a typical size that are used in this case would be 50, 62.5, 85, and 100 microns for the diameter of the core. And then the cladding is going to be approximately 125 or 140 micrometers in diameter. Another type of optical fiber is a single mode optical fiber, and in this case we are using stepped index type of single mode fiber. So here we are using a reduced size of the core. It's the size of the core is small enough to support or to restrict transmission of a single mode. That's why we call these optical fibers single mode optical fibers. So in this case, modal dispersion is completely removed, since we have just single mode, and since single mode transmission avoids modal dispersion, modal noise, and other effects that come with multi-mode transmission will not be present in this type of structure. And an immediate effect was going to be that these types of fibers can carry signals at much higher speeds than multi-mode fibers. So single mode stepped index fibers are standard choice for virtually all kinds of telecommunications that involve high data rates or span distances longer than about a kilometer, and are often used at slower speeds and shorter distances as well, if the budget allows for that. On the picture on the right side, we have a comparison between the single mode and multi-mode fiber from the perspective of the number of modes. So we see that in the case of a single mode fiber, again we have just one single mode, as opposed to the multi-mode where we have different modes that are propagating along the larger core size in a multi-mode fiber. So in the case of a single mode stepped index fibers, the simplest design that's being used is so-called matched cladding fiber. So here we are using a pure fused silica for the cladding, and then for the core we also use pure fused silica that's however been doped by a germanium oxide that's going to change the properties of the core. That's going to change the properties of the fused silica in the sense that the index of refraction is going to be increased. So index of refraction of the core is going to be higher because we doped the pure fused silica with the germanium oxide. Another type of single mode stepped index is so-called depressed cladding fiber. So in this case, the core is a fused silica that's doped with less germanium oxide than that is needed for a matched cladding fiber, and then the inner part of the cladding surrounding core is doped with a fluorine, which reduces its refractive index below that of a pure silica, and finally the outermost part of the core is going to be pure fused silica. So basically we have three layers here. We have the core that has the highest index of refraction because we added germanium oxide to the pure silica, and then we have a red layer that is going to be our cladding, and that material is doped with a fluorine that reduces the index of refraction, and finally the outermost part is going to be pure fused silica that's going to have a higher index of refraction relative to the middle layer that's been shown here in red. Also on the picture here we see the distribution of the index of refraction as we are moving from the center radially towards the edge of each of these different layers. We already talked about the applications of a single mode stepped index fibers. So here we elaborate a little further. So single mode fibers are being used for the long haul high speed telecommunication systems. They're also being used for metropolitan area networks, wide area networks, global area networks, fiber to the home, or so-called FTTH types of applications, etc. So anything that involves larger distances is where this type of optical fiber is going to find its used. Installation and the maintenance of these types of systems that are based on single mode optical fibers may be more expensive due to the complexity of the electronics that's involved, for the simple reason of much smaller dimensions of the core size that we have to deal with in the case of a single mode optical fibers. Now, it's also important to mention an alternative to the glass-based optical fibers, and that is going to be optical fibers that are made out of plastic. So optical fibers that are composed of plastic actually have been in use longer than the glass fibers, and we can have different types of optical fibers that are based on the plastic. We can have multi-mode stepped index and multi-mode graded index type of fibers. And these types of fibers are cheaper than the glass fibers, but they also have certain limited performance characteristics. So obviously plastic has more loss, so it's going to lose more light during the propagation through that type of plastic-based core. So in this case, we are talking about higher numerical aperture, larger core size, and cost that's less compared to the glass-based optical fibers. So there's a whole bunch of advantages and disadvantages. Usually we are talking about applications where the distances are really short. We just need to bypass, move from point A to point B that's just a few feet apart. So that's where these types of fibers based on plastic are going to be find its application. Type of plastic that's being used is so-called plastic clad silica, and as already mentioned, we may have both multi-mode and single mode type of optical fibers that are made in this type of materials. They are generally cheaper than glass-based fibers, but they also have a limited performance as mentioned on the previous slide. What are other important properties or characteristics of plastic-based or so-called plastic-clad silica fibers? It's obviously higher numerical aperture because the size of the core is larger, it's low bandwidth, it's a very tight band radius, it's short length, that's where these types of optical fibers are being used, so less than 10 to 20 meters or just a few feet, but the advantage of these types of fibers is the low cost. So to wrap up this lecture, to summarize the lecture, so we talked about the construction of optical fibers. We have introduced a few different types of optical fibers and different ways how index of refraction has been distributed radially in the optical fibers. So we talked about single mode fibers and multi-mode fibers, and we broke down the multi-mode fibers into so-called stepped index fibers and graded index fibers. We said that the graded index fibers have a superior performance relative to the stepped index fibers because the modal dispersion is significantly reduced through a tight control of the index of refraction of the glass core. We also briefly discussed the single mode fibers that may be either matched or depressed based on the type of materials that are being used to make the glass core and the cladding. And finally, at the end, we also talked about plastic-based, so-called plastic-clad silica fibers that are some sort of cheap alternative to the glass fibers that has much higher loss but lower cost, and it's usually used for shorter distances. This wraps up the lecture number 4, where we discussed the construction of the optical fibers. Talk to you later.